This is 2.1.7, conservation. So to begin with, I'm going to introduce quantum numbers and what they are, and then we'll look at a few particles and write down what the values are for their different quantum numbers. So quantum numbers are things like charge, baryon number, lepton number, and as part of lepton number, there's also the sublepton numbers. And strangeness. There are also things like spin, isospin, third projections of isospin, and various other quantum numbers, but these are not in the scope of the A-level course. So we're only going to look at these quantum numbers. So as a recap, the quantum numbers in an antiparticle are all opposite that of the regular particle. So the charge would be the opposite sign, the baryon number will be the opposite sign, lepton number, etc. will be opposite signs. So if they're positive in the baryons or the regular particles, then they'll be opposite or negative in the antiparticles. Now, let's look at a few different examples, and then we will put their quantum numbers in. So let's do, for example, the proton. The electron, and we will do the anti-muon. Which is the mu plus. So let's look at proton. Proton's baryon number. Is it a baryon? Actually, let me start with charge, because let's keep it the same order as I've done up there. So let's get rid of that. We'll start with charge. So charge of a proton, it's got a positive charge. Relative charge is +1, so put +1. Then its baryon number. Is proton a baryon? Yes. So it's got a baryon number of 1. Then we had the lepton number. So is proton a lepton? No. So it doesn't have a lepton number. And if it doesn't have a lepton number, it also doesn't have sublepton numbers. So let's write down the sublepton numbers here. The electron lepton, the mu lepton, and the tau lepton. So all of these are also 0. And then finally, we've got the strangeness. Does a proton have a strange particle? No. So it's got 0 strangeness. Now let's do the electron. So the charge of an electron is -1. The baryon number of electron, well, electron's not a baryon, so it's 0. Its lepton number is 1. Then its sublepton numbers, it's got an electron lepton number of 1, a mu lepton number of 0, and a tau lepton number of 0. And then because electrons are also not strange, it has a strangeness of 0. Now we'll do the anti-muon. So the charge of the anti-muon is +1. It's still not a baryon, so its baryon number is 0. It's an anti-lepton, so it has a lepton number of -1. And then for its sublepton numbers, it's not an electron type. It is a mu type, but it's anti, so it's negative. And it's not a tau type, so that's 0, and it has no strangeness. So these are the quantum numbers for 3 different particles, and then you can figure out the rest by following the same sort of pattern. So the questions you ask yourself is it a baryon? Is it an anti-baryon? Is it a lepton? Is it anti-lepton? Which type of lepton is it? What's the charge? You just write them out. Okay, next I want to do the conserved quantities. So we've got charge, we've got baryon number, we've got lepton number, and sublepton numbers too. But there's one which is not always conserved. So strangeness is only conserved in strong interactions, which is when they're created, and they're created in pairs. Which means that if a particle is created that has negative strangeness, another particle will be created that has positive strangeness, and the overall strangeness will be 0 when they're created. And in weak, they do not need to be conserved. So not conserved in weak. And that means that it can change, and I'll put in brackets here decay as well, because that's when they decay. So it can change by -1, 0, or +1. And that's quite important because strangeness will not decay by more than those numbers in one go. There would have to be a second order decay to make that happen. Now, a few other things to add onto here are that the decay of 2 particles. So the kaons, and I won't do it as a bullet point actually. Yes? Yes, it can. There you go. So, generally, for the decay of kaons and muons, kaons decay into pions, but that doesn't mean they can't also decay into other things. So sometimes they'll also decay into muons as well, and pions, so it could be a combination. And muons decay into electrons. Now, these examples will be a little bit more complex because you have to think a little bit more about all the conservation laws at the same time to determine what the particles are and why they are that way. So for example, when a muon decays into an electron, you have to consider not only the lepton number, but you have to also consider sublepton numbers and how they get conserved. So what particles also need to be created in that process. And then finally, we'll just do an example of how you show using conservation laws in an exam and how you get the marks. So we'll do example. Show that the decay is or is not possible so you'll be given some kind of a decay. So in this case we have proton decaying into a neutron plus a beta plus an electron type neutrino. Now when you're given this, the first thing I want you to do is draw a line underneath it like so, and then you start to label, or you write down all the quantum numbers. So always start with charge, after charge, then do the baryon number, the lepton number, sublepton numbers, and then finally strangeness if you need to. So let's do this. So charge, so the proton has a charge of 1, the neutron has a charge of 0, the positron has a charge of 1, and the neutrino has a charge of 0. So once we've shown that, we can see that it is conserved because 1 before and it's 1 after. So that is conserved. Then we can do the baryon number. So for proton it's 1, for the neutron it's 1, positron is 0, neutrino is 0. So that's also conserved. Then we can do the lepton number. Proton is not a lepton, neutron is not a lepton. The positron is an anti-lepton, so it's -1. And then the neutrino is a lepton, so we can see it's 0 before, and -1 plus 1 is 0, so it's 0 after, so that's conserved. Then we can do our subleptons, so electron, mu, and tau. So the electron is 0 for the proton, 0 for the neutron. Beta plus, well that's an anti-electron, so it's got negative lepton number there. Then the neutrino, it's an electron type neutrino, so it has a +1 for the electron lepton, and we can see that's conserved. For the mu type, everything here is 0 because there are no muons involved, so that's conserved. For the tau type, again everything here is 0, so that's conserved. Now finally I've left strangeness, because we don't need strangeness to be conserved to say that it is possible or not. However, you can use the conservation or not conservation of strangeness to say whether it is strong interaction or whether it is weak interaction. So if the strangeness is conserved, it may be a strong interaction, but then what you need to see is, are there more strange particles being created or are they disappearing? So if they are being created, then it's a strong interaction. But if strangeness is not conserved, right away you can say that this is going to be a weak interaction. Okay? Now even then, strangeness, when it is not conserved, in one decay, it can only move by -1 or +1 or 0. So then at the end of that, you need to write a little statement to say all the quantum numbers are conserved, therefore it is possible. And that's the end of 2.1.7.